y'all, Darrell Lee Berry Jr. back with some more STEM. We're doing some quantum mechanics today. So we'll go ahead and take a look at some stationary states, as the text says. So basically, this is based upon chapter 2.1 of Griffiths, which those who have been watching the channel, you are familiar with the Griffiths book. You can see the book cover on the previous scene. And what I'll do is just basically go through that section and talk about what stationary states are and a little bit behind the derivations behind it. So previously we looked at a few derivations. We looked at Gaussian integrals. We looked at the expectation value of things and probabilities in the previous videos. So basically this section is starting to take those concepts a bit farther as far as the practical applicability in quantum mechanics. So we talked about the Schrödinger equation, which are right here. What's the pad? Not sure. Let's see here. Right, so this is the Schrödinger equation. And what we'll do, I'll actually make this a capital psi. So this is the Schrödinger equation. An equation to find the wave function that describes the behavior of a quantum particle. And this is equation 2.1 in the book. So the idea is that in order to basically find a wave function that solves this equation, because this is a differential equation, you can see this is a single derivative here with respect to t. This is a second derivative with respect to x. So we need to find a psi of x and t that when you multiply it times IH and take the first derivative of it, it equals the same thing as if we multiply it times h bar squared over 2 and take the second derivative of it and sum it with the potential plus the psi. So basically we're trying to find a psi of x and t that solves that equation. And the process or trick or procedure that this session discusses is separation of variables. So separation of variables basically takes this function of two variables, x and t, and it says we can write that single function as a function of x times a function of t. So the idea would be to try to find out what psi in terms of these two functions of each variable will solve this equation in that manner. So all we have to do is simply plug that in. We see that this is a psi first derivative with respect to t. So if I take d capital psi dt, that'll be d dt of this. When I plug this in, so that'll equal psi of x and b pi dt. And now we have the same thing with respect to x. We have the second derivative. This should be an x. So now what we would do is we would plug this into the Schrodinger equation and see what pops out. So we know what psi of uh, refer to the derivative with respect to t of big psi is. So we have so all we did was take the Schrodinger equation, equation 2.1, and we plugged in the derivatives of capital psi in terms of the separation of variable equivalent. And now we have this. Now to isolate each independent variable, all we have to do is divide psi and pi, and we can see that this will cancel out. We end up with I h bar 1 over pi d pi dt, and we see that this will stay the same. This will stay the same. This will cancel, and we're left with 1 over psi, and both of these will cancel v. Now, the reasoning or the idea that applies at this point is if we look at this on the left, we have an equation that just has the pi with respect to t, and this side only has psi, the lowercase psi, with respect to x only. So we've separated the variables. Now we have two differential equations that are equal to each other, but one is with respect to only t, the other is with respect to only x, and t is time, x is position. So the way this works is if time changes, if time varies, and since time can vary here with no change on this side at all, what this has to mean is that all changes in time will still have to equal whatever this is, whether x changes or not, because time is not included on that side. And the same thing happens to the other side. Anything that happens here with position, if position doesn't change here, no matter what the left side is, it still has to equal the right side. So the only way that can happen is if both of these are constant. So both of these have to be constant so that no matter what happens with position or uh, uh, time, they stay the same. And the variable that they chose to utilize here is E for energy. Reason being, if we look at this, we have the potential here, and this is approaching something to do with the kinetic energy. So let's take a look at this. So I'm going to rewrite this as 2 differential equations. So E equals I h bar 1 over pi d pi over dt. E equals negative h bar squared over 2m b squared psi over bx squared 1 over psi plus v. So here we can go ahead and simplify this a little bit. What I'll do is multiply both sides by psi, and we have e psi equals negative h bar squared over 2m d squared psi over dx squared plus v psi. So now we have two partial differential equations that we can solve. So looking at this left side, we can see that all we have to do is multiply by dt, and we'll actually multiply by everything to simplify it and get just the differential on the side by itself. So I'll do e over I h bar psi of pi equals d pi over dt. And what I can do is I can multiply this by I over I to simplify that side. Multiplying by 1 doesn't change anything. So d phi over dt equals negative e over h bar psi. There's an I here. Do like this hop. And what we can do is we can multiply both sides by dt, and we have d phi equals negative ei over h bar phi dt. And basically what we can do is we can guess what side will solve this. So you've also taken the integral of both sides. So basically, on the left side, when we take the integral of d phi, that ends up just being phi. And what we need on the right side is something that when we take the integral of it, I guess we should say we need something that when we take the derivative of it, it equals this. So basically the integral of f equals f, and the derivative of big F equals little f. So we need to have something that when we take the derivative of it, it equals f, which is inside the integral here. So this part here is our f. So we need something that when we take the derivative of it, it equals f. And two good options for that, when you have something that equals itself plus some kind of thing that is multiplied by, it's either a exponential or a trigonometric function. Either an exponential gives you the same thing back or something similar back, the same thing back with enough derivative as far as trigonometric functions, plus multiply by something that's inside the function. In this case, we'll do the exponential way. So if I have my exponential be this, then if I take the derivative of that, we see that we get psi back, as you always get with the derivative of an exponential. But then you have to take the derivative of the exponent and multiply by that with respect to t, which means that we do get that. So this ends up being the solution for that equation. Now the one on the right is a bit more complicated because we don't know what v is. So the one on the right will have to have a specific v to work with in order to understand what that is. Now, a few details about the importance of separating variables in quantum mechanics is how it relates to the nature of solving the equations. And we'll look at a few of the main three components that the book talks about. And it should be noted, by the way, that this equation here is called the time-independent Schrodinger equation. So that's a time-independent Schrodinger equation because, as you can see, there's no time component, it's just x. And this full one up here is the time-dependent Schrodinger equation, because there's time that is a part of it. So the first thing we can look at is equations solved by separation of variables are stationary. So what that basically means is, at least the way I think about it, I'll put it that way, is sort of how you have like a standing wave where, this section will seem to go up and down, but the wave looks like it's just standing there. Which I understand later is gonna bring about a sort of interesting way that this plays out. But suffice it to say, let's look at how this works. So if we put what we had in our separated equation, it had psi x, psi t, and we were able to solve for psi of t explicitly enough, we can plug that in. And what we can do is we can actually utilize what we did a few videos ago when we actually got the normalization for the equation. So we want to get the normalization, or just the probability density, really. We would do that. And let's see what happens when we plug this in. So if I was to extract the psi squared, we know from before that the mod squared is the complex conjugate times the regular one. And we know that the complex conjugate, what it does is it puts a negative wherever I is. So putting a negative on an I that's already negative will make it positive. And the other one stays negative. So you have one with a negative exponent. So basically this is like one in the numerator and one in the denominator, and they cancel, or at least they equal 1. So that means that we're left with this. So what this means is if we did take the normalization of this, first of all, if we take the normalization of the full psi of x and t, then we also take the normalization of little psi, because they equal up to be the same after the complex conjugate makes the time component disappear. So what this means is that no matter how time changes, x does not change, so the value for x will be what it is. It won't deviate over time, and thus the equation is stationary. That's one thing to point out. They also point out that the expectation value ends up being the same way, in that the example that they utilize is simply utilizing the full uh, definition. So if you remember a few videos ago, we utilized Q as sort of a standalone operator or dynamical component. And we saw before how P, the P operator, is negative I H bar partial with respect to X. So if I was to take the uh, expectation value of Q, this will be psi star to be this. Because if we had it um, capital and we had the exponential in there, there's no x term in exponential. So it simply is a variable compared to this derivative. So the two exponentials will still multiply by each other and come out as one. Therefore, the expectation value is time independent as well. So what that means is that, as the book states it, every expectation value is constant in time. So another thing, which is what I was referring to or getting to earlier, these stationary states are states of definite energy. So you know from classical mechanics that energy is the potential energy plus the kinetic energy. And in quantum mechanics, the potential energy is this. And utilizing the same classical, we can actually multiply this times m over m. And this ends up being 1/2 m squared v squared over m. So this ends up being plus p squared over 2m, because m times v is momentum. We have that squared and divided by 2m. Now, if we look at this, the time independent Schrodinger equation was this. So what this is telling us is that since we have E, and let me actually write this over again. Maybe that's not the best bracket to use. Let's use this bracket. Right. So as we can see, we have psi on each thing. So if we was to cancel outside, we would have E equals negative h bar squared over 2m partial squared plus v. So this then becomes our kinetic energy term. So energy total equals negative h bar squared over 2m partial x squared plus v. And they call, and I'll put this as a similar to. And we call this, I'll write it over one more time. We have E psi equals negative E bar squared over 2m squared x squared plus V psi. So basically, extracting psi out of it, do it that way, we call this the Hamiltonian. So this value here is called the Hamiltonian in that if we put this operator onto psi, it would extract the energy of psi, the total energy, and give us psi back, which is quite interesting. And this actually comes up, it's a very important component in understanding this that comes up later as we move through the chapters. So this book is trying us to get at least to chapter 8. So the book is 12 chapters long. So I've been doing videos a whole lot more often. I'll start doing some through the week and see if we can get through chapter 8 by August, at least. But I may do a few through August. We'll see how it goes. But that's called the Hamiltonian, this operator, because we can put that operator on psi, and it'll give us psi back plus multiply it by the value of the total energy. I'll write this line one more time. And interestingly enough, if we, the way this works is, if we was to actually take the expectation value of the Hamiltonian, let's see what this looks like. So we have psi star, and we know that H on psi gives E psi. And now E is just a value, so we could extract that out the integral. And we know that we're going to normalize this to equal 1. So that equals E. So the expectation value of the Hamiltonian is the total energy. And if we was to do this times squared, we will see that we would just have a squared here. So you end up with an E and you'll still have an H, but there's still a psi on the right. So it'll happen again and you'll just end up with E squared. So this is a very important dynamic that we will look more into later about how this outputs energy. And what this means is, remember a few videos ago when we did the variance and standard deviation, the variance is the standard deviation squared. And this is going to be so this means that there's no variance in the standard deviation or the spread of energy when it comes to these stationary states. So what the book says, every measurement of total energy returns a value of E. Right? So if you have given separable solutions, the stationary states, every measurement of total energy returns E, which is the same value we get if we put the Hamiltonian onto psi, right? And the last thing we'll look at before we close up is the fact that these separate solutions, you can sum them up to get the general solution. Because again, we solve here the time independent Schrodinger equation. But how do we solve for the total equation? So what we can do is we can actually, instead of solving this complicated thing directly that has terms of x and t, we can solve the time independent Schrodinger equation and then recognize that since each of these are stationary states, the way it works is when you add, like we have a stationary state that looks like this, and another one that looks like this, you can add these together and you'll get something, a mixture between them. And the idea is that if you solve for enough of these stationary states and add them together in a precise way, you'll be able to get any general state from properly adding them together. So we can say that big psi x of t is going to be a combination of psi all the way to psi infinity and pi infinity. And the difference here would be I would have to find some constant to multiply them by to keep them normalized to the initial conditions, whatever those initial conditions are. So the way the book would write this is by saying that we'll have the sum n equals 1 to infinity, and we have whatever the constant is that we need to make sure it stays aligned with initial conditions, psi n, and we'll put what h bar. Unless we have that. So basically what we can do is we can find C, we can find the separable solutions psi, we can have an energy, and thus we can actually sum these things to get the overall equation that we're looking for, these overall function that'll solve the time dependent Schrodinger equation in full. So as we go along, we'll look into the details in more depth. And what I may do is come back sometime early in the week. I'm off on, and it looks like my camera froze. Let me see what's going on here. I'm not sure what happened with my camera, but hopefully it was going earlier. But suffice it to say, we'll come back on next week, and I'll go ahead and we'll look more into the book, more into uh, uh, the solutions to the time independent Schrodinger equation, and we'll talk about the infinite square well as we look into that. So thank you all for watching. Make sure you like and subscribe if you haven't already. I'll see you all next week sometime during the week.